In this class, we study computation of potential energy. In the previous class, we learned how to define the potential energy. And potential energy came from the work kinetic energy theorem. And Coriolis work kinetic energy theorem states that the kinetic energy difference is the work. And kinetic energy minus the work is invariant. So this is the reason why we define the potential energy to be the minus work done by the force. In this case, the Hamiltonian is the kinetic energy plus potential energy. That is the total mechanical energy. That is invariant. Alright, so the work is f dot dx from 1a to b, and put the negative sign on it, then it is the potential energy at b. But because this is integral, we need to assign the value of the potential energy at the reference point. Alright. So potential energy is work, attach a negative sign on it, and value at the reference point. And here, this point Q is the reference point, and the position vector of point Q is reference point, and the value of the potential energy at the reference point is necessary to define. However, the physically meaningful one is the work during the displacement. Therefore, this one is related. This one is a minus change in potential energy. So only the change in potential energy is important. So the change in any change, this reference value cancels. It does not contribute to physical variable. Usually, one can choose the reference point where force becomes zero, but it is not an absolutely correct. So this is just convenient convention. For example, a force satisfying inverse scale law decays to zero as r goes to infinity. So in that case, u of r goes to infinity, this is the reference point. There are many, multiple ways of choosing the reference point, and that value is chosen to be zero. But we do not have to stick to this zero value, but this is just for convenience. If we have Hooke's law, the force on a spring is proportional to the displacement from the equilibrium position, and it is usually x equals 0 is chosen to be reference point x0, and the value of the potential energy at x equals 0 is chosen to be 0. But it doesn't have to be 0, it is just for convenience. If we have constant force, it is definitely conservative. In the previous class, we learned that if a force is irrotational, it is always conservative. The surface integral of this form can always be expressed as a line integral along a closed path that is the boundary of the surface. This is Stokes' theorem. And if the force is irrotational, this integral is vanishing. That means for any surface, that means for any closed path, the work done by the force along the closed path is vanishing. That means conservative. And gradient, no gradient, curve. If the force is constant, every derivative vanishes, so it is zero. So constant force is always irrotational and therefore conservative. Constant force example is the uniform gravitational force that is near the surface of the Earth. Then you have potential energy. U of x is u of x0, reference point, minus force dx. And if F is constant, I can pull out this F from the integral. And this is a trivial integral from reference point to arbitrary point. So I have a potential energy that is this, whatever. This is just constant, so it doesn't matter. Yeah, minus F. So potential increases. This if F is parallel to the displacement from the reference point, then potential, this is positive, so potential decreases. So potential increases as if the force is opposite to the displacement. This is the reason why the potential is given in here. Potential has a maximum value near the gradient of potential in this way. This is the gradient of potential, but the force is a minus gradient of potential. So force is opposite to the gradient direction. So let's go ahead. This is still the constant gravitational force. So we have found the u of x up to constant minus f dot x minus x0. In the case of a constant constant force, we substitute minus mg dot x minus x0. Gravitational acceleration is down, and this is along the force. Potential increases as opposite direction. So G is chosen to be minus G of E3 hat. This is E3 hat. So displacement delta x is HE3 from a reference point x0 where it is on the ground. Then if we substitute this one in here, it's minus m minus GE3 hat and HE3 hat and scalar product. So this is MGH. That means as we go in opposite direction to the direction of the force, potential increases. If we follow the direction of force, U decreases. So this negative sign means the displacement must be opposite to the gravitational field to increase the potential energy. We encountered this kind of problem in many times. The pendulum problem. There are two ways of measuring the indicating the position of a pendulum. Usually we use the angle. If we use this vertical direction going above, then this is the angle theta, and we know mgh is the potential energy, and h means opposite to gravitational field. It's opposite to the gravitational field. So that opposite direction is when angle theta is given in here, that opposite direction is this. So h is L cosine theta. Here, this is opposite direction. So h equals L, still L cosine theta. However, it is a down in comparison with a reference point going down. So it is a minus L cosine theta. So if we write in this way, the potential energy relative to this origin is mgl cosine theta, and you can always erase u0. So sometimes you can write it mgl cosine theta, or sometimes you can 2 plus cosine theta, that's fine. 1 plus cosine theta, that's fine. But in this case, minus mgl cosine theta. Restoring force of a spring. We have a force here. I need to put the negative sign on it for the force and the integral. We substitute this one in here, then minus kx dot dx. Integral from the reference point to a certain point. This one becomes a plus. K can be factored out. We have x dot dx. Leibniz formula can be used to combine this. This is total differential of 1/2 x squared. K. Hence, we have 1/2 k x squared minus x0 reference squared. Reference value x0 is usually chosen as 0, and the u of x0 is chosen to be 0. So this one disappears. What I have is 1/2 kx squared. So this is the restoring force of spring. X is the displacement from the equilibrium position. negative sign and k is a positive, so slope is negative. And then the potential energy, when we fix u x0 equals 0 is to be 0, it is probably curved. It doesn't have to be this one. We can draw any kind of form. That shift doesn't matter. However, this is the most convenient representation. Let us consider central force. Central force is a conservative force. We already have proved that it is a conservative force in the previous lecture. But anyway, the proof can be done by evaluating the curve, and that curve was exactly 0. What is the central force? Central force is a force between two objects whose direction is along the straight line connecting the two objects, either parallel or anti-parallel. That doesn't matter. However, it should always be parallel to the line connecting the two objects. So, if we choose the position of the particle to be x and the origin to be the position of the other particle, then the force is always proportional to ER, that is x divided by the magnitude of x, or minus ER. If it is minus ER, it is attractive. If it is a plus ER, it is repulsive. So the central force is always conservative, and there exists a potential, and we don't have to worry about the path. It must be path independent, and we choose a single direction to compute the potential energy. But inverse square law is satisfied by the gravitational force and Coulomb force. Newton's law of gravity and Coulomb's law for electrostatic force, both of them are satisfying the inverse square law. The strength of the force decreases as r increases with the rate 1 over r squared. And it is a central. It has ER hat factor. And there is some strength. Strength is K. And this is an attractive case. Gravitational force is a positive definite. The factor is GMM, gravitational constant and product of two masses. In the electrostatic case, the factor is minus product of two charges, 4 pi epsilon 0. And epsilon 0 is the vacuum permittivity. In either case, the logic is exactly the same. So if you do this calculation in the gravitational case, then in the next semester, your life is very easy, because the theory is a carbon copy, except for the magnetism. That is a little bit difficult in comparison with this. The potential energy of inverse square law, as I already stated, it is central force, the curl F is 0, E rotational force, always conservative. But because it decays as distance increases, so it becomes 0 as r goes to infinity. The simplest choice of the reference point is r goes to infinity. So r goes to infinity, r goes to infinity. There are so many points of reference, but we don't have to worry about it. All of them are all 0. So if you have a particle, capital mass m, and another particle, small mass m, they communicate with each other with the gravitational force, then what you have to do is just to extend the straight line connecting the two particles to approach the infinity, and then you integrate over the straight line from the infinity to the point where this small m is placed. During this integration, the gravitational force attractive, so displacement and gravitational field, they are parallel. Therefore, this is the integration. The work during the integration is a positive, because the work, negative sign on it, that is potential energy. So potential energy must decrease. The rate of decreasing the magnitude of the force 1 over r squared, and the magnitude of the decreasing behavior of the potential energy is 1 over r, because 1 over r is the first order derivative is minus 1 over r squared. Therefore, even before we compute carry out the explicit computation of the gravitational potential energy, we can draw the curve. It should decrease. We know the value of the force is 0, and we choose the reference point to be out to the infinity, and at that point u of r goes to infinity is set to be 0. So gravitational potential must start from 0 as r goes to infinity, and it decreases as 1 over r. So it should have a negative sign on it, 1 over r, and some number. And I guess the overall vector should be identical to each other. So GMF. This will be the answer, but let's see what if it is really is. So we computed this integral, minus f dot dx, integral from infinity to x, and f is minus r squared gmn e to the r, and dx in er dot equals 1, and minus minus, it is a plus. So r squared integral from infinity to r, this integral multiplied by gmn is the answer. We know this one is minus r. Indefinite integral of this is minus r infinity. Then if we substitute r, minus 1 over r, and subtract it, so plus 1 over infinity. That is vanishing. So this is the answer. As I expected, the gravitational potential energy of a particle, small m, with the distance of r, with another particle of capital mass capital M, is this. It is negative. Let us consider the gravitational force due to a uniform circular mass distribution. If capital M is distributed over this ring, which is placed on a plane, we can choose the center of this circle, and we can draw a perpendicular line that is orthogonal to this plane on which the circle is placed. Then we find that this r is the perpendicular distance from this circle to the mass, and the radius of this circle is capital R. We find every partial mass of this mass distribution has equal distance to this small m. That is, Pythagoras theorem can be used. We have radius r and perpendicular distance small r, and the distance between this mass, small mass, point mass, and the partial mass is square root r squared plus small r squared. Therefore, even before we calculate, we can make use of the potential energy, because potential as well as the force, potential energy is also additive. And we say the potential energy of a point particle, this is minus gmm r, this is r, and now we have all of the mass distribution has the distance squared to capital R squared over r. Therefore, the gravitational potential energy of this whole system is minus gmm. The distance is this, r squared over r squared. This is the answer. Am I right? Am I right? Am I right? Yes, I'm right. However, we can make a cross-check with a different method. How? The force between a simple dm, let's use the different notation, because this is a small m, I have m, and the capital M, this is total capital M, and g is the strength, and minus distance r squared over r squared, and er prime. Er prime is the direction, it is this direction. Well, why don't we use different notation? Not er prime, normal vector, and hat, something like that. What I have to do is I have to integrate. This magnitude is always the same. However, this vector depends on the position of small this dm. dm varies. Therefore, it is a little bit complicated. However, they can always be decomposed into, this is the central force. The force must be along this way, and this opposite one applies the same magnitude of force in this way. And if we sum these two, we have this amount that is parallel. So this is anti-parallel, perpendicular component. Two perpendicular components cancel exactly. So only this component is double. So only that component survives. So among the contribution, this is a gravitational force due to this amount. Only this is a theta, cosine theta. This is theta. cosine theta contribution survives and sine theta contribution disappears. So, and then this is the actual direction, which we say it is ER hat. This is along the ER hat. So this attractive force minus ER hat and GM capital M, sum everything up, and the distance. I should put because this is force. This is force. So this is R squared plus R squared. There should be this factor, original factor, and cosine theta. And what is cosine theta? This is theta, and we have R and small r squared plus r squared. So cosine theta is r over square root of r squared plus r squared. So this power becomes 3/2. And cosine, in that case, cosine is replaced with r. That's it. As we have expected, the result is like that. Let us copy that result and find the potential energy. We guessed this potential energy. If I take the derivative of this to find, minus the gradient of a potential to this potential energy, and if I reproduce this result, then that's fine. I don't have to integrate. That we already have the integral. But because I have guessed this, let me just try. Gradient of u of x. However, u of x is actually u of r, function of r only. Capital R is constant. Force equals minus gradient potential energy, and we have minus gradient minus GMM square root r squared plus r squared. There are many components, but we know this force is along the direction of ER, so I don't have to worry about it. This gradient effectively replaces this. Why? The displacement, the derivative should be the displacement. So radial displacement is this. So when I take the derivative, what I have to do is just take the derivative with respect to the radius, along the unit vector along the radius. So I have two negative sign, then ER hat GMM. What I have to do is just take the derivative of r squared plus r squared minus 1/2. Chain rule, ER hat GMM and minus 1/2, and this power becomes this, and then take the derivative of this with respect to r, that is 2r, and 2 cancels. What I obtain is minus ER hat GMM r over r squared plus small r squared 3/2. Am I right? Yes, I'm right. So this is the answer. We could have integrated this one, but the answer is the same as this. So we have obtained the potential energy due to a ring. If I know this, I can do further. Actually, a shell can be decomposed into many rings. So this integration is possible, and actually Newton was the first person who evaluated the force between a shell and a point-like object. He has found that the force between the shell and a point is what? The same as the 2 points with the same mass. This is called the shell theorem. And shell theorem is historically very important because it gave birth to calculus. Calculus was not created by mathematicians. Calculus was created by physicists. And we don't teach calculus. Calculus became the mathematical subject, but in physics, there are so many calculus problems. We do not go very far to consider continuity, as I already told you many times. That is not the physicist concern. We want to find the answer as quickly and as correctly as possible. That's fine. And perhaps you are learning physicist way of doing calculus. In many classes, I have shown very practical calculations. And at some point, it looks like mathematics, but it is not mathematics. It is just a simple trick of calculation. That's it. I am not a mathematician. The shell theorem states that the distribution, if you do this integral, let me just give you the answer only, because after we learn potential energy, proving the shell theorem is much easier than what actually Newton has done. He didn't introduce the potential energy. He computed the force directly. A very complicated calculation. As you know, force has three components, three Cartesian components, because it is a vector. However, if we consider scalar, scalar is a single variable. So the dealing with a scalar rather than a vector is much easier. That's the reason why I postponed the direct proof of a shell theorem until the next lecture. Anyway, this is a shell. Even though it looks like a ring, it is a shell. It's just a cross-section of a shell. There is a radius r, and there's point mass outside. In that case, this is exactly the same. Another case, if this point is inside the shell, there is no communication, no force at all. That's quite interesting. So let me apply this shell theorem. The proof is postponed. If I apply this shell theorem, inside the shell, the point particle does not feel any gravitational force. If f equals 0, then integral of f is always 0, so there is no change in potential energy. Delta U equals 0. Therefore, outside of shell, the potential energy is identical to the point particle case. However, but inside the shell, the potential energy is frozen at the value on the shell. That's the reason why small r is replaced with capital R for any value of small r, that is the distance between the two centers. If it is inside, it is frozen to be the value on the spherical shell. Right. Then if we apply minus ER hat, this derivative with respect to the radius, then you obtain these two results. This is constant. We do not have any force. So that's fine. One step further. If we can consider uniform massive sphere mass m, that means sphere means it is a field. Shell, it is empty inside. In the field, sphere is shell. In that case, potential energy outside is always the same, but inside is a little bit different. Inside, why don't we consider the boundary value when r equals to capital R? In that case, this guy vanishes. And this is identical to the shell problem. So on the border, we cannot identify whether it is a shell if this is mass m, both mass m, this is a sphere. Outside, until we reach the surface, I do not have any way to distinguish shell from sphere. But as soon as I enter, shell does not apply any force. Sphere does, because if we go penetrate the surface, still there is a shell in it. So the mass inside interact with this point particle m. However, this just outside, they don't interact anymore. That's the difference. Because the volume of this is proportional to the mass inside, that is proportional to r cubed. And the distance from inside to there is proportional to 1 over r. These two cancel to reach r square dependence. That's the reason why we have r square dependence inside the sphere, not sphere, inside the sphere. But boundary condition should be satisfied. When it reaches capital R, it should be cancelled. So that this is the only way to satisfy those boundary conditions. But at the end of the day, in the next lecture, we will evaluate this one explicitly. Anyway, if we use this potential energy, we can take the derivative with respect to r, the radial component of the force inside the shell is not vanishing anymore. Inside the sphere. Inside the shell, the force vanishes, but inside the sphere, there is another shell, so this amount of mass applies. That's the reason why we have a heart in the denominator, in the numerator. As a result, if we had two masses, point masses, the potential energy should have decreased to the infinity, minus negative infinity. However, there's a big change from the surface of the sphere, and it is increasing linearly to arrive at the point of surface. So that's quite interesting. This is a remarkable result coming from the shell theorem. And this also applies to the electrostatics. In physics, there's no way to measure the exact magnitude and size of the elementary particle. An elementary particle, for example, electron is one of the smallest elementary particle. It is extremely small. If you compare the interaction between the two electrons, when they approach together, they have repulsive force very much. But for example, electron and proton, they attract very much, and when they approach close enough, it is a very strong attractive force may appear, but that is not the fact. If it is the case, everything must disappear. Every positive, negative charge will meet and annihilate. But it is not the fact our world is stable because of the another natural force, fundamental force called the nuclear force that is strong, either strong or weak. And furthermore, perhaps the electron is not a mathematical point. This is quite important. We employ mathematical expression for our language, but the nature does not tell you electron is a point. That's a point is a mathematical idealization, and that is nothing to do with the real world. And when we approach, such kind of singularity does not appear. That means electron must have some size, very tiny, but it has a finite size. In that case, the force does not have any singularity. This is a very nice picture of the natural cutoff of the divergence in reality. The regulator that regularizes the unphysical singularities, Coulomb singularities, and gravitational singularity as r goes to 0, this unpleasant infinity appears, but that does not exist at all in nature. Exercises, their applications in high school level problems. This one is these problems are quite useful in the sense that we do not have to solve the equation of motion. Equation of motion is usually the second order differential equation. However, as far as the magnitude of velocity at speed is concerned, we can make use of the fact that the total mechanical energy is conserved. In that case, our life becomes very easy. The conservation strictly determines the sum of the mechanical energy. I mean, the kinetic energy plus the potential energy should be the same whenever. So these are quite simple problems. And now we return to the same problem. Previously, we just used some trick to evaluate those integrals, but why don't we integrate directly? Recall ring point mass problem. Previously, we used the fact the magnitude of the force at every point should be something like that with the differential, right? However, the component perpendicular to the direction that connects the center and the point mass, perpendicular component cancel, and only the longitudinal component is a parallel component that survives. That's the reason why we have multiplied the additional factor that is cosine. But let's see what happens if I do the explicit calculation with the integration. We introduce a unit vector. This is a circle. I have x-axis. I introduce the phi. The angle is too small. Phi. Then this point, this radius r. This point is r. Cosine phi. E1 hat. C2 sine phi. Let me call this one to be E phi hat. The mass of the small tiny one that can be divided into d phi, and we have the arc length is r d phi, and the sum of the arc length is the 2 pi r, and we assume that this capital M is evenly distributed over 2 pi r. So dm must be m times d phi over 2 pi, right? So, and y minus x, what is y minus x? Okay. This one, r E3 hat. We have E1 hat and E2 hat, and this one is E phi hat. Perhaps we should have used a rho instead of phi, but that doesn't matter. That is integrated over. Right. And y minus x, this is the distance. This is x. This is a y minus x. So this is what we know already. And force is this. Right? Substitute these numbers in it. So y minus x is this one subtracted by this, and that is given in here. And dm is replaced with this. Capital M survives here, and d phi over 2 pi. We are ready to evaluate the integral, but here r, small r, capital R fixed. In this integral over phi, E3 phi appears phi. This is cosine, either cosine or sine. If we integrate over E3, E3 is independent of phi. E3 is along this direction, independent of phi. Therefore, E3 integral is the E3, except that the integration is just 0 to 2 pi, phi to 2 pi. So 2 pi is 3. However, this one is vanishing because of sine phi, d phi, or cosine phi, d phi, from 0 to 2 pi, 0 to 2 pi. They are all vanishing. So goes away. They go away. Only this one survives as we expected. Immediately I have r in here. denominator here. That's it. Exactly the same as what we have expected. Alright, so we can make use of this idea. We know how to evaluate the gravitational force on a ring, but this ring, radius of ring, can be increased. Alright, I can evaluate the potential energy due to a disk. That's next problem. If I want to evaluate the disk, then the mass, we have a rho, and this thickness of this annular region is d rho. In that case, what is the area? This area is, this length is 2 pi rho, and thickness is d rho. So this area is 2 pi rho d rho. And this is a pi total differential of rho squared. Leibniz told you. So the area is, total area is 2 pi r. So mass is distributed evenly over 2 pi r. And what is the differential mass of the annular region of the thickness d rho at radius rho? This is this. And we can make use of the result we just obtained previously. For this one, we just replace this m with dm because it is a thin one. So this one is m, but what I need to do is replace this m by dm, and anything else to be copied, I can copy the result and the dm, substitute this one, and then I have this integral. What should I do? Integral table. You can just use this. If you don't agree, why don't you take the derivative? If you take the derivative, you'll find this, then you have completed the integral table. And then substitute y as rho square. And this completes the integral. And the final result for the force is of the form. And why don't we take the limit? Small r is much greater than the disk radius. Disk radius is small r, and this distance is this is capital R, and this is small r. And small r is much greater than the radius of the disk. In that case, m is here, small m is here. It's nothing but a 0.2 point particles. Let's see if it is true. If r is much greater than capital R squared, then it can be approximated in this form. This is according to the binomial expansion, 1 plus x to the alpha. When x absolute value is less than 1, it can always expand it as alpha x plus alpha minus 1 x squared to factorial and so on. So if you consider the first approximation, the power is this 1 plus r squared minus r squared minus 1/2. So 1/2 appears here. In that case, 1 cancels. What I really find is this 2 cancel, and finally we obtain the gravitational force due to 2-point masses. Next, what happens if I have this radius is much bigger than this perpendicular distance small r? So this is a flat world, and you are just standing on a flat world. Then what you have to do is just take the limit capital R goes to infinity. Oh, 0! Too easy. It is just, this is the final result. We can replace this one with this surface mass density. mass per unit area, then it is expressed in this way. It is just constant, and the constant strength is proportional to the mass density of this big plate. This one is also used in the electrostatic case. When you consider the electrostatic case, it is a 4 pi epsilon 0 and charge product. And in that case, you will find it is proportional to the charge density. All right? And actually, in that case, it is sigma over 2 epsilon 0. And sigma is a charge per unit area, pi r squared. In the next semester, in the General Physics 2 course, you will find exactly the same problem. Anyway, if you want to understand what really happens in the expansion formula for the binomial expansion, you should be able to take the derivative for the not a polynomial, but x to the alpha, where alpha is a real number. And that can be done if you know how to take the derivative of exponential function. And it is straightforward to verify this, and perhaps this might be the last chance for you to verify this. You will have to apply this formula in your lifetime for so many times, but I can see so many people are not able to prove this, and sometimes they copy the formula and apply to a problem that cannot be applied. That's the problem. If you want to copy mathematical formula, then just follow the strict rule. You just copy the formula without condition and you will fail many times. That's the reason why I derive everything I use. I do not prove in mathematical way. I do prove in my accuracy, in the level of my accuracy. So if you follow me, you can prove any mathematical formula that are strictly used in physical problems and engineering problems without any problem. They do not require any such kind of rigorousness like the mathematics textbook tells you. That's it for today.